Hi, Bobcats. We're going to take a look at some of those solutions to the Schrodinger equation that have been developed, and we're going to take those solutions and use them to figure out where the electrons are in an atom. The reason we would like to describe this arrangement of electrons in an atom is because the electrons determine an atom's chemistry. So if we can have a good description of the electrons in an atom, we can make some good predictions about the chemistry, what sort of bonds an atom would like to form, and what sort of chemical reactions it's likely to undergo. With the quantum model, we describe the electrons as being located in orbitals, and these orbitals are going to be three-dimensional spaces that are centered around the nucleus of an atom, where there's going to be a high probability of finding the electron, and the electron will have a particular energy when it is in that orbital. And we're going to have four types of orbitals that are used by real atoms. Those would be S, P, D, and F orbitals. In theory, since there's an infinite number of solutions to the Schrodinger equation, there's an infinite number of types of orbitals, but all of the atoms that we have in our periodic table use just S, P, D, and F. So those are the ones we're going to look at. Since we have an infinite number of possible orbitals, we need some way of organizing those orbitals and keeping track of them. We generally organize them at two levels. We're going to organize them into shells and subshells. A shell is all of the orbitals that have the same energy, if we're talking about a hydrogen atom. And then a subshell is all of the orbitals that have the same energy and roughly the same shape. At the end of this chapter, we're going to look at something called quantum numbers, and we're going to say that all of the atoms in a shell have the same quantum number n, and all of the atoms in a subshell have the same quantum number n and l. Wow, there's a lot of data crammed onto this one slide, so let's see if we can interpret some of this. First of all, there are four types of orbitals. So that's our first column over here in the table. We have S, P, D, and F orbitals. The S orbitals are shaped like a sphere, and those are the ones that are shown up at the top of this diagram, or it's the one shown at the top of this diagram. Whenever you have an S orbital, it occurs as a set of one. It's a singleton. It's the only one in the set. The next type of orbital is called a p orbital, and it's shaped like a dumbbell. It has these two lobes. Sometimes in class I'll demonstrate this by blowing up two balloons and tying them off, and then I'll tie the two balloons to each other, and then that's pretty much the shape of one of these p orbitals. But the thing about the p orbitals is that you never have one of them by itself. You always have three of them taken together. So they always occur as triplets. So any subshell that's a p subshell has three orbitals in it. The d orbitals tend to look like two p orbitals that are stuck together to form a clover leaf. But remember, each one of these lobes is three-dimensional, so it's like a balloon. You've got four balloons stuck together. And the d orbitals occur as a set of 5. There is one d orbital over here on the very end that has a little different shape to it. It looks like a p orbital with a donut around its middle. But when you get a set of d orbitals, you always get 5 of them together. So a d subshell has 5. And Fs have even more complicated shapes to them. You might want to Google that if you're curious about what they look like. A lot of them look like 2 of these clover leaves stacked on top of each other, so you have 8 lobes. The one that looks like this dz squared orbital is a p orbital with 2 donuts around its middle, so we get some really weird shapes. And the Fs always occur as a set of 7. I'd like for you to take a look at the numbers that are here and the pattern on them. When we're looking at how many orbitals are in a subshell, this is going by the odd numbers, 1, 3, 5, and 7. you'll find that when we look at these solutions to the Schrodinger equation, or orbitals, and electrons in the orbitals, there'll be a lot of very simple patterns to the numbers like this, that these guys are going by the odd numbers. And then when we go to put electrons into these orbitals, the most electrons that we can put into one orbital is 2. So in order to figure out the maximum number of electrons in one of these subshells, we're going to take the number of subshells and double it. So 1 becomes 2, 3 becomes 6, 5 becomes 10, and 7 becomes 14. It's possible to get for these subshells to be in different shells. For instance, we can have a 1s subshell, which means it's the s subshell in the first shell, versus the 2s subshell, which means it's the s subshell in the second shell. And this number out in front is what later we're going to call n, or the principal quantum number. As n gets bigger, or as this number out in front gets bigger, the orbitals get bigger. So for instance, if we were to try to draw a 3s orbital, it would be bigger still. And that trend also holds with the p's. This is showing a 2p subshell up top, and then a larger 3p subshell down below. So the bigger that principal quantum number out front, the bigger the orbitals will be. So when you look at the solutions to the Schrodinger equation and you get all of these orbitals and you arrange them into shells and subshells, you can end up with orbital diagrams that look something like this. A shell would be all of the electrons, or all of these orbitals that have the same number out in front. So for instance, if we were looking at the 4th shell, we're going to have a 4s subshell, a 4p subshell, a 4d subshell, and a 4f subshell. Now I've labeled this at the top as being a many electron atom because it turns out that when you have more than one electron present in an atom, the orbitals lose some of their degeneracy. Degeneracy means that orbitals have this, or electrons have the same energy. So degeneracy, that simply means that they have the same energy. And if you're looking at this diagram, all of the orbitals in a subshell, for instance, all of the orbitals in the 6d subshell have the same energy, but not so for all of the orbitals in the 6th shell. The 6s has a lower energy and the 6p is a little bit higher, and then the 6d is the highest that's shown on this particular diagram. If this was truly the hydrogen atom, anything that was labeled 6 would all be on the same level. But this energy ordering of the orbitals and these subshells will be used when we go to write up an electron's, or an atom's electron configuration. So for instance, let's say we wanted to write the electron configuration for something like sodium, which has 11 electrons. We can fill the electrons into this energy level diagram as long as we start with our first electron in the lowest energy orbital. Each orbital is symbolized by one of these horizontal lines. We can put at most 2 electrons into the same orbital, and when we put them in there, we have to put them in there in opposite directions. So for instance, if we're going to start putting 11 electrons into this energy level diagram, we'll start down here with the 1s at the lowest, and we'll symbolize the electron with a half arrow. The second electron has to go in pointing the opposite direction. Now we've taken care of 2 of them. To put in the next of these 11 electrons, we need to go to the next lowest energy orbital, which is up here at 2s. So we'll put a couple of electrons in there. That takes up 4 of the 11. That leaves us 7 to go. So the next lowest subshell is the 2p. So I'll put one electron in here. Now, if I have more than one degenerate orbital, I want to put the electrons in them by themselves first. So the next couple of electrons should go in this way. So far I've used 1, 2, 3, 4, 5, 6, 7. This is 7 electrons. I still have 4 more to go. So here's number 8, number 9, and number 10. And I still have 1 electron left to place, so that's going to have to come up here into the 3s subshell. So using this energy level diagram, we figured out how to arrange those 11 electrons. But normally these electron configurations are written out a little bit differently. We're going to start by writing the designation for the orbital, starting with the lowest energy one, which is the 1s. And then as an exponent, we're going to write how many electrons went into that subshell. So 1s2 indicates this subshell right here. Then our next lowest energy subshell was the 2s subshell, and we put 2 electrons in it. And so that's indicating this guy. The next one after that is 3p. Whoops, sorry, that's not a 3, that's a 2. 2p. And we put 2, 4, 6 electrons into the 2p. And then that highest energy subshell that we occupied was 3s, and we put just a single electron into it. So when we write out what orbitals the electrons are arranged in this manner, we're going to call that an electron configuration. On the previous slide, I used all of these rules, but I did want to present them to you in one coherent spot. The Aufbau principle is the rule that says we need to start by putting electrons into the lowest energy orbital that's available, and then when that's full, work our way up to the next lowest energy orbital. The Pauli exclusion principle is what tells us that we can put at most 2 electrons into any one orbital. By the end of this chapter, when you know about quantum numbers, we can recast the Pauli exclusion principle to say that each electron must have a unique set of 4 quantum numbers, and then that limits us to putting 2 into any given orbital because of the spin quantum number. And then Hund's rule says that when we have a set of degenerate orbitals, such as the collection of 2p in the 2p subshell, we are going to put 1 electron into each orbital first, and then only pair them up with opposite spin when there are no longer any empty degenerate orbitals available. So our objective for this video was to use the quantum model to describe the arrangement of electrons in an atom, to start writing their electron configuration. The good news is that in the next couple of videos, we're going to look at simpler ways to write electron configurations. You don't have to have one of those energy orbital diagrams or orbital energy diagrams. In fact, you can just look at the periodic table to figure out how to write some element's electron configuration.